last classes, we have seen very basics of OPAMP. Okay, so what should be the input impedance, what should be the output impedance, how why it is called as OPAMP, and which type of feedback is better, and what is virtual ground. All that we have seen in the previous class. Okay, in the today's class, I would like to introduce some more parameters. Okay, some more parameters which will be defining the efficiency of your OPAMP. So some of the parameters are like, again, these are very important. Okay, so whatever parameters I'm doing now, it's like it might be some repetitions will also be there, and along with that you may also learn some new parameters of OPAMP. So the first parameter is differential gain, which we have already seen. Differential gain, which is given by AD. Okay, so how will you find the differential gain? So here I'll have the OPAMP, inverting terminal, non-inverting terminal. This is the output. These are the two inputs. This is my V1 and this is my V2. So V0 is nothing but AD times of VD. VD is nothing but difference between these two. Okay, where VD is nothing but V2 minus V1. Why V2 minus V1? Because non-inverting terminal voltage minus the inverting terminal voltage. So VD is equal to V2 minus V1. Okay, so if I want to define differential gain is nothing but the ratio of output voltage to the difference in the inputs. Okay, V0 by VD. Okay, ideally this should be equal to 0 because V1 this terminal voltages will be this terminal voltages will be equal to same V1 and V2 for the negative feedback system. V1 and V2 will be equal to same. So this differential gain should be infinite. Okay, AD ideally it should be infinite. Okay, so VD is equal to 0, so AD is equal to V0 by 0, it will be equal to infinite. So ideal case, the differential gain value should be equal to infinite. This is what the first parameter. This differential gain I have already explained you. Okay, so it is nothing but the gain of the amplifier circuit. Okay, then comes the common mode gain. Common mode gain, which is denoted as AC. Okay, AC is nothing but the common mode gain. So what do you mean by common mode? Common mode in the sense both the inputs, whatever inputs you're giving to the negative inverting terminal and the non-inverting terminal, both will be same. Okay, both will be connected to the same voltage source. Okay, so both will be connected to the same voltage source. If this is V1, okay, let me write as Vin. So if this is Vin, even this also will be equal to Vin. V2 will be equal to Vin. Okay, if both the signals are same, then actually your output should be equal to 0. But as I mentioned, it will not be equal to 0. Along with the difference, it will also amplify the average between the two signals. Average between these two is given by V1 plus V2 by 2. Okay, so VC is said to be the common average between the input voltages V1 plus V2 divided by 2. That is nothing but the common for the common mode signals. Maybe VD might be 0, so it may not get amplified, but the average between these two may get amplified. Okay, so V0 will be equal to AC into VC. Okay, AC into VC. Okay, but ideally this should be equal to 0. Okay, the output voltage V0 should be equal to 0. The reason behind that is it should only amplify the difference between the signals. Okay, but what is happening because in the practical case it will not be just take the difference, it will also take the average between the signals. So that is governed by VC. So VC value should be equal to 0. If VC is equal to 0, or VC value ideally this should be equal to 0. But practically it may not be equal to 0. So that is the reason what we'll do, we will adjust the offset voltage. Okay, offset voltage will be adjusted in such a way that the V0 value will be equal to 0. Okay, so this AC is said to be the common mode gain, which is given by AC is equal to V0 divided by VC. V0 divided by V naught divided by Vc. Okay, so this is what the common mode gain. Common mode gain. Okay, AC is nothing but the common mode gain. Okay, and ideally this value should be equal to 0. AC value should be equal to 0. Common mode gain value should be equal to 0. Okay, the reason behind that is you should not have any input voltage. Okay, so that your output will be equal to 0. So ideally this value should be equal to 0. AC should be equal to 0. Okay, this is the ideal value. Anyway, I'll list out all the ideal parameters, but here when I'm taking the parameters, then and there I'm explaining you what will be the ideal value of that particular parameter. Okay, then comes common mode rejection ratio. Common mode rejection ratio. CMRR. Okay, common mode rejection ratio. So as I've already mentioned, when you are applying both the voltages as same, the output should be equal to 0. But what is happening? We are not getting output is equal to 0, but you may get some voltage practically because of the average between the two input signals. Okay, it may take average between the two input signals. So that is the reason you may have some output voltage. So common mode rejection ratio, it tells us how efficiently the OPAMP is able to reject the common mode signals, and it is defined as the ratio of the differential gain divided by the common mode gain. AD is nothing but the differential gain, which we have seen before, the first parameter, differential gain, and AC is nothing but the common mode gain. Okay, and ideally your CMRR should be equal to infinite, ideal value. Okay, why? The reason is AC will be equal to 0. So AC is equal to 0 in the sense AD by 0 will be equal to infinite. So ideal case, the common mode rejection ratio value should be equal to infinite. Okay, so this is what the third parameter. Coming to the fourth parameter, it is sleeve rate. Okay, sleeve rate. What it will tell us is, it indicates how fast the differential amplifier reaches its output. Okay, so if I'm giving some input, okay, if there are any variations in the input, how fast the output is varying with respect to time, that is given by the sleeve rate. Okay, so the sleeve rate is given by SR is equal to dV naught by dt. Okay, how fast the output, how fast the differential amplifier reaches its output. Okay, if there are any changes in the input.
Note, ma'am.
Huh? What? How fast sleeve rate will tell us how fast the output is changing in the op-amp. Okay, so that is given by dV naught by dt. How fast, how will you calculate the fastness? It will be with respect to time. So dV naught by dt. Okay, so within no time the output should reach, the output should change. Okay, so that is the reason. Ideally, the time required to change in the output should be very minimal. It means that dt will be very less. So in ideal case, the sleeve rate value will be equal to infinite. Why infinite? Because dt is very small. Okay, dt in the sense change in time. Change in time should be very small. It means that if the change in time is small, then the output will reach fast. Okay, so it will tell us how fast the output is changing. Okay, so for fastness we will just calculate in terms of time. Okay, so that time required to change the output should be very less. So ideally it should be equal to 0. So since ideally its value is equal to 0, the sleeve rate will be equal to infinite. This is what the fourth parameter. Coming to the fifth parameter, all these are like we will use to define the performance of the op-amp. Okay, next one is power supply rejection ratio. Power supply rejection ratio, in short we'll write as PSRR. Okay, so it is defined as the ratio of change in input offset voltage due to change in supply voltage. That's supply voltage. See, if you just recall, this is my inverting terminal, non-inverting terminal. Here we'll be applying plus VCC and minus VEE. Okay, and here we'll provide the input V1, V2, and we'll calculate the output. So the common, power supply rejection ratio in the sense, see when you make V1 is equal to V2 same, or V1 is equal to 0 and V2 is equal to 0. In either cases, the output should be equal to 0. Okay, but what will happen practically, it will not be same. Okay, and what we'll do, we'll change the offset voltage. Okay, so offset voltage will be changed so that the output will be made equal to 0. Okay, so this power supply rejection ratio, see additionally along with V1, V2, you also have an additional inputs VCC and VEE. Okay, so this power supply rejection ratio will give us how much change is happening in VIOS. VIOS in the sense input VI. Okay, VI. One second. Okay, so PSRR, it will tell us what is the change in the VIOS. VIOS is nothing but the input offset voltage. Hope you understood why input offset voltage will be there. Input offset voltage will be there in order to make output is equal to 0 when both inputs to the inverting terminal and the non-inverting terminal either they both equal to 0 or they both are same. Okay, so in that case we'll get VIOS. So here power supply rejection ratio.
Complaint, yes, complaint.
Okay, change in VIOS with respect to change in VCC. In the sense, if there is any change in VCC, how that voltage will affect this VIOS, that will be given by power supply rejection ratio. Okay, by making the other one constant, maybe V will be kept constant, or in other way, either you can calculate by using this, or PSRR can be calculated by taking change in VIOS divided by change in VE. Change in VE, if there are any changes in VE, how it is going to affect VIOS, that will be given by PSRR. Maybe the other one will be constant. Other one might be constant. Okay, so this PSRR, it should be ideally equal to 0 because the VIOS value should be equal to 0. Okay, because when you are not giving any, you are not applying any voltage, input voltage, the output should be equal to 0, and when both are equal to 0, both are same, V1 and V2 are same, then also the output should be equal to 0. In the sense, the VIOS offset voltage should be equal to 0, but practically it will not be the case. But ideally it should be the case. Okay, so the ideal value for your PSRR will be equal to 0. PSRR will be equal to 0. Okay, then comes the last parameter, input bias current. Input bias current. It is given by the average between IB plus and IB minus. Average input bias current, it is denoted with IB. IB is nothing but IB plus IB minus. Average between IB plus and IB minus. What is this IB plus and IB minus? I'll show you now. So you know that this is what your op-amp. Okay, this is my V1, this is my V2. Here I'll take V0. This is the inverting terminal and this is the non-inverting terminal. If you just recall the ideal op-amp, so you'll have like this, right? Ideal op-amp equivalent circuit. So it is nothing but Zi. So you know that ideally Zi should be equal to infinite. Infinite in the sense it will not allow the current to pass through it. So that's why this terminals will not draw any current. This, let me name it as IB minus, and this let me name it as IP plus. Okay, so as Zi is equal to infinite, this terminals will not draw any current. Okay, I'll reiterate it once again. So input bias current, it is nothing but the average current between the inverting terminal current and the non-inverting terminal current. Okay, but ideally if you see the op-amp equivalent circuit, so as you see from the terminals, you will have some impedance. That impedance I'm naming it as Zi. Zi ideally it should be equal to infinite. Infinite in the sense there is more resistance here. Since there is no more resistance here, what it will do, it will not allow the current to flow through it. Okay, IB minus and IB plus, whichever I have considered here, the current should not flow through it. Okay, but the IB practically it won't be equal to 0, but ideally it will be equal to 0. So this IB input bias current is nothing but the average between these two currents. So ideal case, ideal value of your input bias current should be equal to 0, because this terminals will not draw any current. So IB will be equal to 0. So these are some of the parameters of your op-amp. Okay, hope you people are following. Ideal op-amp characteristics. So whatever we have listed up, I will list out all those parameters once again here, and this is very important. Okay. So coming to the first parameter, as you know, input impedance. Okay, let me write this. All of you note down the parameters. Input impedance. Input impedance is infinite. Input impedance is infinite. That is, Zi is equal to infinite. Okay, so I have already explained you why Zi should be infinite. Next, output impedance is 0. That is, Z0 is equal to Z0 is equal to 0. Z0 is equal to 0. The third one, infinite voltage gain. Infinite voltage gain. Okay, so infinite voltage gain, AD should be equal to infinite. Next parameter is, as I've already mentioned, here I'm just listing out the parameters. Say already I've given all the explanation related to this gain and all. Here I'm just explaining you the, here I'm just listing out the parameters. zero offset voltage. So zero offset voltage, VIOS should be equal to 0. Okay, so I've given clear explanation what is this VIOS. Okay, the fifth parameter. Then the fifth parameter is infinite bandwidth. Infinite bandwidth. Okay, so infinite bandwidth because this implies that it has to amplify all the signals from 0 hertz to like infinite hertz. Everything it has to amplify. Okay, so that is what this bandwidth is infinite indicates. Okay, so you know that the op-amp will amplify the signals, right? So it ideal op-amp, it has to amplify all the signals, DC signals to like infinite frequency signals, all that signals it has to amplify. That's why the bandwidth is considered to be ideally the bandwidth should be equal to infinite. Then comes CMRR, common mode rejection ratio. Okay, so it should be infinite, or I'll write in the other way, infinite common mode rejection ratio. Infinite CMRR, common mode rejection ratio, or I can write as CMRR. Generally we denote this as this with rho. Rho should be equal to infinite. Okay, so this is a next parameter, and the next one is infinite sleeve rate. Okay, dV naught by dt. Sleeve rate SR should be equal to, ideally it should be equal to infinite because the time required to change the output should be very less. So SR will be equal to infinite. Next, power infinite not infinite, it is zero. Zero power supply rejection ratio. Zero PSRR. Okay, so PSRR, as you know, it is defined as change in VIOS with respect to change in VCC or VE. Okay, so that should be equal to 0 because VIOS value should be equal to 0 ideally. Okay, then ninth one, no effect of temperature. Okay, it means that see, if you just take the op-amp, as I've already mentioned, it will be made with transistors, resistors and all. Okay, so if it's get heated up, there will be a lot of electron hole pairs generated, because of which what happens, the normal operation of the transistor will change. Okay, so here ideal for an ideal op-amp, we have to consider that temperature is not going to affect it. Okay, that is what the next parameter, and the other one is zero input bias current. So you know that input bias current IB is equal to IB plus IB minus divided by 2, average between the terminal currents. Okay, so ideally this value should be equal to 0 because as the op-amp is considered to have infinite input impedance, it will not draw any current. This is very important for the sake of applications when we will be doing the like all the parameters whatever we have seen before. All that is very important when we will be analyzing the applications. Okay, so these are the parameters which you need to list out. So in the exam they may ask you explain ideal characteristics of op-amp. So in that case you should be in the position to explain all the parameters. Okay, so this is one question, and the other question may be explain the following. So explain the following, they may ask recently the chemistry cycle, whatever exam they have written, in that they have asked explain the following. In that they have asked common mode rejection ratio, sleeve rate, common mode rejection ratio, sleeve rate, and common mode gain. Common mode gain. Okay, so a common mode rejection ratio in the sense you need to explain with respect to rho, which is nothing but AD by AC. Related to that, you need to explain sleeve rate in the sense dV naught by dt. Okay, so this with respect to this you need to explain common mode gain in the sense AC value should be equal to 0. So related to AC is nothing but V naught divided by Vc. What is Vc? Vc is equal to V1 plus V2 by 2. Okay, so all this this is what they have asked, and they have given it for 6 marks. So if you just explain this much, in the sense like you have to write in words also, and even the equations are very important. Okay, so if you explain all that, you'll directly get 6 marks. Okay, and one more question they have given you. What are the ideal parameters of OPAMP? Okay, so that was one question. So for that he has given 4 marks. So since it is 4 marks, even if you write any 4 ideal characteristics, you'll get 4 marks. Okay, so as I was mentioning, these are very important things or the topics for your IA, or if you had external, even in external you would have got questions related to this. Okay, so hope this is clear to all of you. Have you all understood the ideal parameters?
Yes, ma'am.
Yes, ma'am.
Okay. Now I'll go to the important part. Applications of OPAMP. So as I've already mentioned, OPAMP will amplify the signals. Along with that, it will also perform some mathematical operations like adding, subtracting, differentiating, integrating. All this will be performed using the OPAMPs. So we will list out all the applications here, and we will also study in detail. And here one important thing what you need to do is you need to remember the circuits. Okay, circuits remembering is very important. Okay, so coming to the applications of OPAMP, first let us see the first application, ideal inverting amplifier. Ideal inverting amplifier. Ideal inverting amplifier. See, inverting amplifier is specified. Okay, and you need to consider the OPAMP. See, for all the applications, we'll consider the OPAMP to be ideal itself. Okay, we'll consider the OPAMP to be ideal only, and we will analyze the applications. So first application is inverting amplifier. Okay, inverting amplifier in the sense, you need to provide input only to the inverting terminal, and the non-inverting terminal should be grounded. Okay, so as I mentioned, you need to remember the circuit. So draw the OPAMP. As I mentioned, first take the inverting terminal and then the non-inverting terminal. This is what the basic diagram. Okay, to this you need to connect an additional components, and along with that you need to also provide inputs and all. Okay, so since it is OPAMP, as I've mentioned, will be using the negative feedback. So from V0, it is fed as an input to the inverting terminal. Okay, and here what we need to do, we need to provide one resistor, and through the resistor I'll connect the voltage. Let this voltage be Vi. Okay, Vi or whatever name you want to give, you can give. Okay, so let me name this feedback resistor as RF and this resistor as R1. And since it has to act as inverting amplifier, the non-inverting terminal will be grounded. Okay, grounded in this is the voltage here will be equal to 0. Okay, grounded in this is the voltage here will be equal to 0. And let me name this voltage as VA, and let me name this voltage as VB. These are the terminal voltages. So can anybody tell me what I can derive from this virtual ground concept? according to the virtual ground concept, what will be the VA and VB voltages? Okay, what is VA voltage? VA voltage is nothing but voltage at this point is somebody quickly answer me. What will be the voltage here? It is grounded. Grounded means what will be the voltage here? What will be the voltage here, ma? This is grounded. So what will be the voltage here? Grounded means what will be the voltage? Isn't it 0 volts? This is grounded. It means that the voltage here will be equal to 0 volts. And according to the virtual ground concepts, this terminal voltages, when you have the negative feedback, the terminal voltages here will be same. It means that VA is equal to VB is equal to same. So since VA is equal to VB, so VB voltage will also be equal to 0 volts. This is the first equation. This I'll name as equation 1. This is very important equation which you need to know. Okay, so according to the virtual ground concept, VA will be equal to VB. This voltage and this voltage will remain same. Okay, and now you need to further analyze the circuit. Since I have connected the voltage here, let me consider the current is flowing in this direction. So let me name this as current I1. Okay, so it's coming here and it has to split in these two terminals. This is nothing but IB minus, and this let me name as IF. Okay, and at this node, I will apply KCL. According to the Kirchhoff's current law, currents entering is equal to the currents leaving. I1 is the current entering, that will be equal to currents leaving. Currents leaving is nothing but IF is the leaving current and IB minus is also the leaving current. But here you know that IB minus will be equal to 0. IB minus will be equal to 0 because ideal op-amp will not draw any current. So ideal case, IB minus is equal to 0. Since IB minus is equal to 0, this I1 will be equal to IF plus 0, which will be nothing but I1 plus, I1 is equal to IF. Okay, so this I'll name as equation 2. Okay, then come back here. So with respect to this ground point, you know what will be the voltage here. This voltage is nothing but VI, and this voltage is nothing but VB, and this voltage is nothing but V0. Okay, so now what I need to do, I need to find the current I1, current IF in terms of node voltages. So current is flowing in this direction, so this terminal will be positive and this will be negative. Entry will be considered as negative and exit will be considered as negative. In the same way, current is flowing in this direction, so this will be positive and this will be negative. Now what we need to do, we need equation for I1. So I1 is equal to I1, you know that V is equal to IR, I is equal to V by R. And what is V with respect to the terminal voltage? This plus corresponds to this VI and this minus corresponds to VB. So I1 is nothing but VI plus VI minus VB divided by resistance there. What is the resistance there? R1. R1 is the resistance there. This is my I1 equation. And you know that VB is equal to 0. So I1 is equal to VI minus 0 divided by R1. So I1 is equal to VI by R1. So this equation I'll name it as 3. This equation I will name it as third equation. Next, IF. IF also I want to represent in terms of node voltages. So IF is nothing but V by R. I is equal to V by R. V is nothing but with respect to the terminal voltages plus VB minus V0 divided by RF plus VB minus V0 divided by RF. This is what the equation for your IF. And you know that VB is equal to 0. So VB is equal to 0 in the sense IF is equal to 0 minus V0 by RF. So this is nothing but minus V0 by RF. This I'll name as equation 4. Now what I'll do, you have equation 2 as I1 is equal to IF. Now what I'll do, I'll substitute 3 and 4 in 1. Sorry, in 2. 3 and 4. Third equation, I1 equation. I1 equation is nothing but Vi by R1. IF equation is nothing but V0 by RF, minus V0 by RF. These two I'll substitute it in 2, second equation. So I1 is nothing but Vi by R1, that is equal to IF. IF is nothing but minus V0 by RF. So here what I need to do, I need to find V0 voltage. So V0 will be equal to, rearrange the terms, you will have as minus RF by R1 into Vi. Minus RF by R1 into Vi. This is what the final signal. So if you just observe V0 is equal to something into Vi. Okay, so you need to properly choose RF and R1 in such a way that the signal will be amplified. This is the input is 5 volts. Then by properly choosing RF and R1, you can increase its strength. This 5 volts can be improvised. Okay, and here you can observe that there is a negative sign. Okay, so this negative sign indicates that the output is 180 degrees phase shift. 180 degrees phase shift. It means that if I am providing the input signal in this way, this is my input Vi. Vi is in this way. Vi is in this way. Then my V0 will be okay, my V0, this is my V0. V0 will be amplified. So if you just observe, the frequency is not changing, only the amplitude is changing. But if you just observe, it is inverted, 180 degrees out of phase is there. So this is what, these are the waveforms of your inverting amplifier. So since you're getting a negative sign when you're providing input to the inverting terminal. See, if you just observe, we are providing input to the inverting terminal. To the inverting terminal, you have applied the input, and the non-inverting terminal is grounded. When you are giving input to the inverting terminal, and when you are making the non-inverting terminal grounded, what is happening? Your output is amplified, but you're getting a negative sign. So it indicates that it is having 180 degrees phase shift. That's why only it is said to be the inverting amplifier circuit. So in the exam, they may ask you, explain the inverting amplifier circuit of an op-amp. Then first thing, you need to draw the diagram. First mention what is the voltage of the non-inverting terminal. Then this according to the virtual ground concept, VA and VB voltages, what will be the voltage? Then what is like you need to properly specify the currents I1, I2, I1, IB, dash, IF, everything. Write the equations and finally get the output equation, V0 equation. Everywhere we'll be finding the output equation only. All applications will be finding the output equation only. So finally write the output equation and finally draw the waveforms like this. So this is what your op-amp as acting as an inverting amplifier. Hope this is clear to all of you. Understand one application properly. The rest all will be very simple. Only thing is you need to remember the diagram here, and here I've just specified how to remember the diagram as well. Okay, first draw the basic op-amp, then RF and R1 will be there. Any circuit you take, RF and R1 will be there. Okay, and where you need to give the inputs, you need to check. That's how some additional components will be added to the basic op-amp circuit. That's it. Okay, so this is how you need to add to make it work as an inverting amplifier. Hope this application is clear. Anybody hasn't understood this application, please tell me so that I'll explain once again. Because if you understand this application, the other applications are similar. Only thing is you'll be adding some additional components, resistors, inductors, all that. That's it. That is the only difference. Otherwise, the analysis part will remain same. Analysis part will remain same. Hope it's clear. Hope this application is clear. The second application is non-inverting amplifier. This is asked in the recent exam for 6 marks. This as it is, explain non-inverting amplifier of one OPAMP. This is directly given for 6 marks. Okay. So what is that? You need to have the basic circuit first, minus plus V naught here, and we should have the negative feedback. This I'll name as RF. This is the R1, and that's all. That's all the basic circuit. Now you need to add additional voltages to this. So if you just observe the question, it has to act as non-inverting amplifier. It means that the inverting terminal should be grounded. Okay, and to the non-inverting terminal, you need to give voltage VI. It means that the voltage here will be VI. Here I am providing VI voltage. If you are getting confused with this symbol and all, you need not draw that. You can just take this input voltage as VI. Both are same only. Okay, however you are comfortable, you can just draw it. So this is nothing but the ground connection. With respect to this ground point, I am providing VI voltage so that this voltage is VI. Okay, and let me name this voltage as VA and let me name this as VB. Okay, VB. And you know that according to the virtual ground concept, VA will be equal to VB. And first of all, what is VB voltage? VB is nothing but, what will be the voltage here? What is this voltage? VB, right? VB voltage is nothing but VI. Okay, because directly I am applying voltage here, and this is nothing but the terminal voltage of non-inverting. This is nothing but the non-inverting terminal voltage. So VB is equal to VI, and according to the virtual ground concept, always this terminal voltages across the op-amp will be same. It means that according to virtual ground concept, VA is equal to VB. That will be nothing but VI, because VB is equal to VI. Therefore, since VA is equal to VB, here VA will also be equal to VI. Okay, so this I name as equation 1. Okay, now again I need to assign the current direction. So this is the ground connection. So this current I will name it as I1 in this direction, and this will be IF, and this will be IB dash. IB minus. Okay, so again apply KCL at this node. Apply KCL at this node. Okay, so currents entering is equal to currents leaving. IF is the entering current, and I1 and IB minus are the leaving currents. So IF is equal to I1 plus IB minus. Anyway, IB minus value is equal to 0. We know that IB minus is equal to 0. So therefore, IF is equal to I1. This I will name as equation 2. Okay, this I will name as equation 2. Again, I need to represent this I1 and IF in terms of node voltages. So current is flowing in this direction, so this will be positive and this will be negative. Current is flowing in this direction, so this will be positive and this will be negative. So first I'll write the equation for I1. So I1 is equal to plus VA minus 0. This is grounded. It means that the voltage here is nothing but 0 volts. So VA minus 0 divided by R1. So that is the equation for I1. Say again, let me write. Or if you have any doubt, I1 is nothing but this voltage and this voltage. So minus 0 plus VA. This positive sign corresponds to this node voltage and this negative sign corresponds to this node voltage. So I1 is equal to minus 0 plus VA divided by R1. Both will yield you the same equation. So finally, your I1 is nothing but VA by R1. So let me write the equation. I1 is equal to VA by R1. But you know that what is VA? VA is nothing but VI. So VI divided by R1. VI is nothing but the voltage what you are giving. Whatever signal you are giving to that, it will be VI. Okay, so this I'll name as equation 3. Otherwise, I'll write one more time. I1 is nothing but VI by R1. This I'll name as equation 3. Now come back to the circuit. IF also I want in terms of node voltages. So IF is equal to minus VA plus V0 divided by RF. Okay, and again I will write this here. IF is nothing but minus VA plus V0 divided by RF. And you know that what is VA? VA is nothing but VI. Here we have got VA. VA is nothing but VI. So that I'll substitute in this. So V0 minus VA. VA is nothing but VI divided by RF. Or I will write as IF is nothing but V0 minus VI divided by RF. This I will name as equation 4. Okay, I've got equation I1 in terms of voltage and IF also in terms of voltage. So now what I'll do, I'll substitute 3 and 4 in 2. Substitute 3 and 4 in 2. Okay, so what is the second equation I have? I1 is equal to IF. So I1 is nothing but VI by R1. VI by R1, that is equal to IF. IF is nothing but V0 minus VI divided by RF. Now what we'll do, we'll rearrange the terms. So take VI by R1 is equal to V0 by RF minus VI by RF. See, what I need to do is I need to just simplify this expression so that I will have the equation for V0, final equation for V0. Okay, so just take this plus VI by RF to the other side. So V0 by RF is equal to VI by R1. This you take it to the other side. So here I have minus. So if it goes to the other side, it will be plus VI by RF. Now what I'll do, V0 by RF is equal to VI. In both the terms I have VI, so I'll take VI common, so that I'll be left out with 1 plus RF by 1 plus R1 divided by 1 by RF. Okay, so now what I'll do, I want equation for V0, so that I will take this RF to the other side. So V0 is equal to RF into VI, 1 by R1 plus 1 by RF. Now what I'll do, see this RF I will take it inside once again. So V0 is equal to VI into RF by R1 plus RF by RF. So this RF and this RF will get cancelled. So V0 will be equal to VI into 1 plus RF by R1. This is the final equation. So by properly taking RF and R1 values, you will get the output voltage which will be amplified. And here if you observe, you don't have any negative sign. Okay, so you have not got any negative sign, because here whatever input you are giving, it is given to the non-inverting terminal. So if you just observe, the input is given to the non-inverting terminal and the inverting terminal is grounded. That's the reason you have not got any negative sign. Okay, so it will be in phase. Okay, so if you want me to draw the output waveform, this is VI. Next V0. V0 will also be in the same way, but it will be the amplified version. amplified version. Okay, so that's all the difference. So this is VI and this is V0. Okay, hope this is clear to all of you. That's all the non-inverting amplifier.
Yes, ma'am.
Okay.
Ma'am, I have a doubt.
Tell me, ma'am.
Isn't the gain of an op-amp infinity, ma'am?
That is the ideal case.
So Vout should be like infinite, no, ma'am? The waveform, like.
See what we are doing. I'll tell you one thing here. We are giving the feedback, right? We are giving the feedback. So this feedback is given only to control the output output voltage. So otherwise, what happens? Let me just draw that waveform. I've already explained you related to this. Wait, let me just reopen it. See, this is your ideal op-amp, right? So ideal op-amp, what will happen? It will take the difference and it will find the output. V0 is nothing but AD types of VI. So VD, the difference between these two will be taken and it will amplify. So what happens? Since the op-amp ideal op-amp gain is infinite, what happens? As you are increasing the VD, it will go to infinite. Okay, so what happens? But practically that will not happen. So what will happen here is until certain voltage, whatever your input you are giving. So this is nothing but the VD and this is nothing but the VD versus V0 graph. Okay, so what happens here is the as VD is increasing, V0 will also increase. Okay, after certain voltage, what happens is it will saturate. It will not exceed more than that. Okay, so here it is saturating, right? So in order to control this output, we are giving the feedback. And here specifically I'm giving the negative feedback because negative feedback will stabilize the system. Okay, so as I'm increasing VD, what will happen? It has to increase and it has to go to infinite, right? So in order to avoid this condition only, we are going with the negative feedback. Negative feedback, what happens? The input and this will get subtracted. Okay, so that is the main reason why we are going with this negative feedback. This we are doing only to control the output voltage. Hope I have answered your question, Kaustubh.
Yes, ma'am, understood.
So now I'll go to the next application. Third application, it is voltage follower. This is very simple circuit and even the analysis is very easy. So the circuit connection is like this. You need to remember again. Minus plus. Voltage follower circuit. Voltage follower circuit in the sense, whatever input you are giving, it should be their output. So for that, what you need to do is, this is the inverting terminal and this is non-inverting terminal. So here what I'll do, I will short both the input terminal and the output terminal, inverting terminal and the output terminal. This is V0, and here I will provide the input. PI is provided in this non-inverting terminal. So this is the circuit. This is a circuit of voltage follower. This is grounded. Okay. That's what I'm telling you. If you are not comfortable with this, you don't draw. Okay, but don't make mistakes. Okay, it's left to you. Okay, so whatever voltage you give here, that should reflect at the output. It means that if you give 5 volts, I have to get 5 volts. If I give 0.5 volts, I should get 0.5 volts. If I give 2 volts, yeah, you should get 2 volts. That is what the function of the circuit. So now let us analyze whether your V0 is equal to Vi or not. Okay, so let us analyze. So this are the terminal voltages. Let me name this terminal voltage as VA and this terminal voltage as VB. And we know that VB is connected to the VI. So VB is equal to VI. Okay. And since according to the virtual ground concept, your VA will be equal to VB. Okay, VA will be equal to VB. It means that your VA voltage is also equal to VI. So this is the first thing where we have connected the input. So VB voltage is nothing but this voltage. This voltage is nothing but VB, or it is also equal to VI. So here VA is equal to VB again according to virtual ground. These two are not virtual in the sense it's not. It will not exist, but it is. It will be. It is valid. Okay, so that's what the virtual. So VA, VB. So VA and VB will be same. So VA is equal to VB. So VA is equal to VB. You know that what is VB? VB is nothing but VI. So VA is equal to VI. VA is equal to VI. This I name as equation 1. Then, if you just observe, this V0 and this VI are shorted. They're just connected with a wire. It means that whatever voltage you have here, the same voltage will be here also. So it means that V0 is equal to VA. Okay, and you know what is VA? VA is nothing but substitute this VA in this equation, second equation. So substitute 2 in 1. So V0 will be equal to VI. Okay, so whatever input you are giving, that will be appearing at the output. So this is the circuit which will work as voltage follower. Voltage follower means whatever voltage you are giving, that will be at the output. Okay, hope this is clear to you. There is no amplification happening here. Whatever input you are giving, that is appearing at the output. So this is how the connection should be. Okay, hope this is clear to you. Right? Is the circuit clear?
Yes, ma'am.
Yes, ma'am.
I'll go to the next circuit. Summer. See, first we have seen inverting amplifier, non-inverting amplifier. Then we have seen the voltage follower circuit also. And I have mentioned that this op-amps can also be used as used to perform some mathematical operations. So the first one is summer circuit, summer or adder circuit. Anything is same. So whatever inputs will be given, that should be added. So that is what the meaning of this. Okay, so for that, again, the circuit is in this way, minus plus op-amp. And the negative feedback will be there, RF. And here what we'll do is we will connect all the three or how many inputs you want you can give. Okay, so I'm just taking 3 inputs. I'm just giving 3 voltages here. So what this has to do, V0 should be equal to whatever inputs you're giving, that all the input voltages should be added. Maybe infinite, I don't know how many voltages I'll connect, how many inputs I'll give here. That many, all that voltages should be added. Okay, so that is what this circuit has to perform. So in order to get that, again this is given in the question paper. Okay, so based on this, they have given 4 plus 8, 4 plus 8, 10 marks question, 4 plus 8, 12 marks. 12 marks question has been given based on this circuit. Okay. So first thing is they have given as explain adder circuit of an op-amp using an op-amp. Okay, so for that they have assigned 4 marks, and one more question they have given. They have given some equation. I'll show you that also. They've given some equation and they have asked you to design the circuit. How to design also I'll tell you. But for this circuit, whatever we are going to study now, for that they have given 4 marks. Okay, so First I'll draw the circuit. So instead of giving the inputs directly, I'll give it through the resistor. This is my R1, this is my R2. Like this, how many inputs you want, you can give. V3, V4, how many inputs you want, you can give by using the resistor as well. So this, whatever we are doing now, it comes under knowledge level 4. Okay, knowledge level 4 in the sense applications. Okay, apply and then analyze. Apply in the sense like whatever concepts you have studied, you will be applying that, and analyze in the sense you'll solve some problems based on that. Okay, so let me just take 3 inputs, V1, V2, V3 are 3 inputs, and I have not connected it directly through the resistors. I have connected R1, R2, R3. Okay, and this I will ground it. This is the circuit now. Okay, so again we need to analyze this circuit. So let me again take the VA, VB voltages. This I'll name as VA, this I'll name as VB. Can anybody tell me what is VB? What is VB voltage?
0.
0. And according to the virtual ground, VA is equal to VB. So since VA is equal to VB, here VA will be equal to 0 volts. This I'll name as equation 1. Then I will take the currents. So let me name this current as I1. Let me name this. See, whatever I1, I2 I am introducing now. Otherwise, the basic circuit, whatever. I'll just tell you once again. This is my basic circuit. This is my basic circuit. Okay. So now what I'm doing to find out the output voltage V0, I'm introducing some additional variables. Those additional variables are nothing but VA, VB I'm introducing. So VB is equal to 0 volts. So VA will be also equal to 0 volts. Then what I'm doing, I'm also introducing the currents. This current is I1, this current is I2, and this current is I3. And let me name this current as IF. And this current, as we were taking it as IB minus, let me take it in the same way. So again, I will apply KCL at this node. Okay, and if you just observe this node and this node, both are same only. Or else, if you have any doubt with this, what you can do is, you can write it in this way also. You can draw it in this way also. Both are same only. Both are same circuits only. If you have any doubt that initially I have drawn the diagram in this way, right? In this way I have drawn the diagram. This is my RF and this current I have taken it as IF. So here I am saying that this node and this node are same because it is just connected with a wire. So if you just have any doubt to identify, what you can do is you can just connect it in this way. Okay, remove this, erase this, and connect it in this way. It's the same circuit only. Okay, fine. Now I need to apply KCL at this node. Okay, so KCL at that node is nothing but currents entering is equal to currents leaving. So I1 is entering current, I2 is entering current, I3 is also entering current, and IB minus and IF are leaving current. So I1 plus I2 currents entering, sum of all the currents entering into the node is equal to the sum of all the currents leaving the node. So what are the currents leaving? IF is leaving and IB minus is also leaving current. Okay, so I1 plus IF, I1 plus I2 plus I3 is equal to IF plus IB minus. But you know that IB minus will be equal to 0. Okay, so the terminals of the op-amp will not draw any current, so IB minus will be equal to 0. So this equation will reduce to I1 plus I2 plus I3 is equal to IF. This I will name as equation 2. Okay, now I want, see, I have got equations in terms of current, but what I want equation in terms of voltages. So what I'll do, again, I will try to represent I1, I2, I3, IF in terms of node voltages. So current is flowing in this direction, so this is positive and this is negative. Current is flowing in this direction, so this is positive and this is negative. Current is flowing in this direction, so this is positive and this is negative. Current is flowing in this direction, so this is positive and this is negative. So I1 current is nothing but I1 is equal to I is equal to V by R, V is equal to I R, I is equal to V by R. V is nothing but the voltage across this resistor R1 with respect to the node voltages. So this plus corresponds to this V1 and this minus corresponds to this VA. Okay, so I1 is nothing but V1 minus VA divided by resistance there. Resistance there is nothing but R1. In the same way, I2 is nothing but the current in this resistor R2. This is your R2 resistor. I2 is nothing but current in this resistor R2. So this plus corresponds to V2 and this minus corresponds to V1. Okay, let me just redraw this once again because it is congested. Maybe you are not understanding it. I will redraw it once again. No problem. V1, this is R1. R2, here I am giving V2 current, V2 voltage. R3, it's connected here, V3. Okay, so this current I have named as I1, this current I have named as I2, this current I have named as I3. And if you observe, current is flowing in this direction. Entry will be considered as positive and exit will be considered as negative. In the same way, here also positive, negative. Here also positive, negative. Here also positive, negative. Okay, and I1 is nothing but voltage across the resistor R1 with respect to the node voltages. So V1 minus VA divided by R1. V1 minus VA divided by R1. In the same way, I2 is nothing but, can anybody tell me I2 equation? Can anybody tell me I2 equation? I2 is nothing but the current flowing through the resistor R2. Can anybody tell me what will be the equation here?
V2 minus VA by R2.
Very good. V2 minus VA. I2 is nothing but V2 minus VA divided by R2. Okay, because positive, negative. No, this is positive and this is negative. This positive sign corresponds to V2 and this negative sign corresponds to VA. Okay, so plus V2 minus VA divided by resistance there R2. In the same way, I3 is nothing but V3 minus VA divided by R3. I3 is nothing but V3 minus VA divided by R3. Next, IF is nothing but current through resistor RF. So with respect to the node voltages, plus VA minus V0 divided by RF. Plus VA, this plus corresponds to VA and this minus corresponds to V0. IF is equal to plus VA minus V0 divided by RF. Okay, now what I'll do, I'll substitute VA value. VA I've got as 0 volts. So since I've got VA is equal to 0, so V1 minus 0 by R1, which will be nothing but V1 by R1. This I'll name as equation 2. V2 minus VA, so V2 minus 0 divided by R2, which is nothing but V2 by R2. This I'll name as equation 4. Next here, V3 minus 0 divided by R3, it is nothing but V3 by R3. This is equation 5. Here again, VA minus V0, VA value is 0, 0 minus V0 divided by RF. So this will be equal to minus V0 by RF. Okay, so this name I'll name as 6. So now what I need to do, I need to substitute 3, 4, 5, 6 in 2. I1 equation, I2 equation, I3 equation, IF equation in here. So here, now what I need to do, substitute 3, 4, 5 and 6 in 2. What is that second equation? I1 plus I2 plus I3 is equal to IF. So what is I1? I1 is nothing but V1 by R1. I1 is V1 by R1, I2 is V2 by R2, I3 is V3 by R3. And IF is minus V0 by RF. All that I'll substitute here. I1 is nothing but V1 by R1. I2 is nothing but V2 by R2. I3 is nothing but V3 by R3. That is equal to IF. IF is nothing but minus V0 divided by RF. So again you rearrange. What I'll do, I'll take minus RF to the other side. So V0 is equal to minus RF into V1 by R1 plus V2 by R2 plus V3 by R3. Okay. Now what I'll do, I'll take this RF also inside. So V0 is equal to minus, let it be RF also inside. It means that it will be RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 into V3. So this is the output equation of the given circuit, and this is very important. You have to remember this equation as well. Okay, you have to remember the equation, this equation as well to solve the problems. Okay, so this is the output equation. So you may ask me a question, ma'am, you said that I have to get addition of all V1, V2, V3. I didn't get. So to get that, what I'll do, I will choose R1 is equal to R2 is equal to R3 is equal to RF is equal to some R voltage. So V0 will be equal to minus of RF is R only, R by R into V1 plus R by R into V2 plus R by R into V3. Okay, so this R and this R will get cancelled, this R and this R will get cancelled, this R and this R will get cancelled. We will have V0 is equal to minus V1 plus V2 plus V3. This is the final equation. You may ask me one more question. Mom, this addition is fine. Why we are getting negative sign? Okay, so we are getting negative sign only because if you just observe the circuit, how is the circuit? See, V1, V2, V3, it is connected to the negative terminal. The non-inverting terminal is grounded. That is the reason whenever you give input to the inverting terminal, the output will be obviously like it will be inverted. In the sense, it will have 180 degrees phase shift. That 180 degrees phase shift is denoted with this negative sign. With this negative sign. Hope this is clear to all of you. That's all with respect to the summer circuit. Is this clear? Yes, anywhere, any doubts you can ask me. Any doubts in this application? How OPAMP is used as adder circuit is fine? No doubts. Okay, fine. So I'll just give you one question now. Note on the question.
ಅದು ಗಾಡಿಯಲ್ಲೇ ಬಟ್ಟೆ ಇದೆಯಾ? ಇನ್ನು ತಗೊಂಡಿಲ್ಲ. ಚಪ್ಪಲಿ ಹಾಕೊಂಡು ಹಾಕ್ತೀನಿ.
I'll give you one question. Find the output voltage of below circuit. This is what the question, and here he has given the circuit as well, and he has given the circuit like this, minus plus. Minus 4 volts, minus 2 volts, plus 3 volts. This is 4 kilo ohms, 4 kilo ohms, 4 kilo ohms. Okay, and then feedback resistor, its value is 6 kilo ohms. P0 is here, and this is grounded. This is what the circuit he has given. So first thing, whenever you get such questions, you need to identify which circuit is this. Which circuit is this? Which circuit is this now?
Adder.
This circuit. So I've told you that you need to remember the equation, right? So this equation, you need to remember this equation. That's what I've told you, right? So using this equation, you need not derive once again. You can directly use the equation. So what is that equation? V naught equation you have as V naught. We know that. What is that equation? V naught is equal to minus of Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3. Okay, so what is R1? R1 he has given us 4 kilo ohms. R2 also he has given us 4 kilo ohms. R3 also he has given us 4 kilo ohms. And Rf he has given us 6 kilo ohms. And then what else he has given? V1 he has given us minus 4 volts. V2 he has given us minus 2 volts. And V3 he has given us plus 3 volts. You know everything, just substitute it in this equation. So V naught will be equal to minus of Rf. Rf value is 6k divided by R1. R1 is 4k into V1. V1 is minus 4 plus Rf. Rf is 6k divided by R2. R2 is 4k into V2. V2 is minus 2 volts plus Rf 6k divided by R3. R3 is 4k into V3. V3 is 3. You need not write volts here. Now you simplify everything. So V naught will be equal to, so this kilo, this kilo, this kilo and this kilo will get cancelled, this and this will get cancelled. 2 3s are 2 2s are. Same here, 2 3s are 2 2s are. 2 3s are 2 2s are. So 2 1s are 2 2s are. 2 1s are 2 1s are. Here 2 1s are, this will be 1.5. So just multiply it, 3 2s are 6 and minus I have, so minus 6. Minus into plus minus, 3 1s are 3. Plus into plus, it is plus only. 3 into 1.5, it is 4.5. Okay, simplify this. V naught will be equal to minus 9 plus 4.5. It will be minus 9 plus 4.5. So it's nothing but minus 4.5. Minus into minus, it will be plus. So V naught will be equal to 4.5 volts. Okay, so this is how you have to solve the problems. Hope this is clear to you. Any doubts you have in this problem? Only thing is you need to remember this equation. That is what you need to do. This equation you need to remember. All the equations, not only this, when you take this in non-inverting amplifier, non-inverting amplifier is there, no? All the final equations are required. Okay, so why that final equation is? 1 minute now. Hope this problem is clear to you, right? Huh?
Yes, ma'am.
So like I'll just stop my class now. Again on Monday I will have the class. Tomorrow and after tomorrow it's holiday. So we'll have class again on Monday. Okay, fine. We have already we have seen 4 applications. Again, I think we have 4 more applications like subtractor, differentiator, integrator, and the same circuit can also be used as comparator. So all these 4 circuits we'll see in the next class. Okay, so that's all for now.